Hello, I am Dr. Deepthi and we are studying different concepts from maths under the heading Decreations Mathematics. We have been looking at the broad topic of linear algebra and our focus has been matrices. Let us look at some basic types of matrices. In earlier episodes, we have looked at scalar matrix, identity matrix, which are basically subtypes of a square matrix. Right now, let us look at symmetric matrix. So, a real valued square matrix such that the condition Aij is equal to Aji is followed. In other words, what does it mean when I say that Aij is equal to Aji? For example, A12 is equal to A21. Correct. I am talking about transpose. Transpose of this matrix is equal to itself. So, A transpose is equal to A. Now, here is an example of a symmetric matrix. As you can see, the element, now which is this element? Row 2, column 1. So, A21. And which is this element? Row 1, column 2. So, A12. So, can you see both of them are equal? Similar cases with A31 and A13. Also, if you see here, A23 and A32. So, this is just by observation you will be able to recognize a symmetric matrix. And then there are certain properties. It has to be a square matrix because when we are making a statement that its transpose is equal to itself, it will have to be a square matrix so that the number of rows and columns need to be equal basically. Now, when you have the condition that A inverse into a given matrix A is identity, here we can substitute that A by A transpose and so we get A inverse into A transpose or vice versa gives you identity matrix. Now imagine that there are two symmetric matrices and if you are adding them, what is it going to yield you? The resultant matrix, do you think it will be symmetric? Try visualizing another symmetric matrix here and try adding it in your mind and let me know what you get as the answer. Correct. It has to be symmetric. Similar cases with subtraction. Now, regarding the product of two matrices, two symmetric matrices A and B, if the condition of being commutative, that is AB is equal to BA, is valid, then you see that the product is also symmetric. Similarly, if a matrix is symmetric, then its integral power, such as a square, a cube, etc., or you can generalize and say a raised to n, where n is an integer, is also symmetric. And if the inverse of a symmetric matrix exists, that is also symmetric. So some interesting properties of symmetric matrices here. Now what will happen if instead of the condition A transpose is equal to A, if you have another condition A transpose is equal to minus A? Well, you will have a real skew-symmetric matrix. So this square matrix having all real elements is skew-symmetric. That means its transpose is equal to negative of that matrix. So what statement can we make in terms of the elements? We can say that Aij is equal to minus Aji, as you can see here clearly. Which is this element? This is second row first column, that is A21, and which is this element? It is first row second column, A12. Can you see? They are negative of each other. Similar situation with A31 and A13, or which is this element? It is third row, second column. So A32 and A23. So if you try to add two skew-symmetric matrices, obviously it will also yield another skew-symmetric matrix. Same thing with subtraction and same thing with scalar multiplication. It's not difficult to uh, visualize, right? Just multiply it by a scalar. These elements will remain to be 0, and rest of them, since, for example, if I multiply it say by 5, then this will be minus 10, this will be plus 10. This will be 20, this will be minus 20. So everywhere the condition is still remaining valid. So these are the real skew-symmetric matrices. Now, in case of complex valued matrices, they have their equivalents in terms of Hermitian matrix, etc. So we will be talking about it in some upcoming episodes. So today we'll stop here. Thank you.